Hello everyone, welcome to me, Learning Rust. Today, after finishing the Chapter 8 exercises, we'll continue with Chapter 9 and learn about errors. Errors are a fact of life in software. Yep. So Rust has a number of features for handling situations in which something goes wrong. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you'll discover errors and handle them appropriately before you've developed your code to production. Deployed your code, sorry. Rust groups errors into two major categories: recoverable and unrecoverable errors. For a recoverable error, such as file not found error, we most likely just want to report the problem to the user and retry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array, and so we want to immediately stop the program. Most languages don't distinguish between these two kinds of errors and handle both the same way, using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result for recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error. This chapter is calling panic first and then talks about returning result values. Additionally, we explore considerations when deciding whenever to try to recover from an error or to stop execution. And basically, what I think is that panic should be only in debug mode and maybe in like core language functionality. Like, you shouldn't have a panic unless you did something that's like wrong in the core language specification if you're in production. Yeah, basically panic is really good for debug, where you can just stop the program and print out some messages, some information, maybe do a core dump so you can debug it. But yeah, in production you should not have any panic. Every possible panic in production is bad software engineering, in my opinion. Okay, let's start. Unrecoverable errors with panic. Sometimes bad things happen in your code and there's nothing you can do about it. In these cases, Rust has the panic macro. There are two ways to cause panic in practice: by taking an action that causes our code to panic, such as accessing an array past the end, or by explicitly calling the panic macro. In both cases, we can cause a panic in our program. By default, this panics will print a failure message, unwind, clean up the stack, and quit via the environment variable. You can also have Rust display the call stack, and when a panic occurs, to make it easier to track down the source of the panic. Okay, unwinding the stack or aborting in response to panic. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. However, this walking back and cleaning up is a lot of work. Rust therefore allows you to choose the alternative of immediately aborting, which ends the program without cleaning up. Memory that the program was using will then need to be cleaned up by the operating system. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting upon a panic by adding panic equals abort to the appropriate profile sections in your cargo toml file. For example, if you want to abort in panic in release mode, add this. Okay, so let's try it out. And I see we already have this code. So let's cargo new chapter 9. And then we code into chapter 9. Great. Okay, now we have this, and we will just replace it by a panic that will say I'm panic, and just add this. Okay, and if I just run this, cargo run, then I get I'm panic. And if I go to the cargo toml file and do a profile, let's see if just profile works. Panic equals abort, and then we'll try to run this. Cargo check failed. Okay, probably we need a profile debug. Will this work? Failed. Release. Okay, looks like it didn't fail. If I do cargo run now, it'll still fail, and if I do cargo run release, it hangs. Okay, yeah, I can't even control C out of it, so let's delete this. So if I panic at release, then it crashes. So let's see what kind of profiles do I have. Cargo, no release here. Okay. Debug. Okay, let's see without profile. Will it work? Do this. Okay. Let's try to run this not in release mode. Okay, and now just process didn't else successfully 101. And if I remove this, what we have here? Oh, unused manifest key. Package panic. And also it was unused. So I need to go to profile. Let's see, maybe there are some profiles we can see here. Let's see. Profile. Okay, let's see what kind of profiles are dev. Okay, profile dev with panic abort. Let's try to run this, and it. Okay. So I don't know why. I need to check. Oh, maybe because of this. No. So when setting the panic abort thing, it just hangs in my system. I'll check offline if there's something I can do about it. Let's just make sure that I can run. Caused by access denied. Ooh, something is really wrong here. Maybe it's the unwinding. It can't compile now because of this. Okay, I think it just takes a lot of time for the OS to clear things up. This is strange because in C, if you just quit, then everything exits really fast, and all the memory is freed by the OS. So if anyone knows why this happens, why it takes so much time for the program to end, just let me know. I'll continue, and I will not use this profile abort thing. Okay, so if I'm calling panic, I have the same error. It says that if I want to see a backtrace, this is the environment variable I have to set. Okay, so let's continue. The call to panic causes the error message contained in the last two lines. The first line shows the panic message and the place in our source code, which is, let me up here. This is the place in the source code. And where the panic occurred. Yeah, indicates that the second line, fifth character of our source main RS file. In this case, the line indicated is part of our code, and we go to that line. We see that panic macro call. In other cases, the panic call might be in code that are called calls, and the file name and the line number reported by the error message will be someone else's code, where the panic macro is called, not the line of our code that eventually led to the panic call. We can use the backtrace of the functions the panic call came from to figure out the part of our code that is causing the problem. We'll discuss backtraces in more detail next. Okay, so basically, as I said before, you shouldn't get panics when using libraries. It's okay to get, this is expected to get panics if you use core Rust functionality. That means you have to fix some things, that maybe you're using things wrong. But if you write a library, I don't think you should throw panics unless you're in debug mode, and even then I'm not so sure. But yeah, let's go. Let's start. Let's look at another example to see what it's like when a panic call comes from a library because of a bug. So let's just print this. Let's clear the screen here and move it back down. And we have let v equals vector 1, 2, 3. And then I'm accessing 99, which is not there. So let's just run this. And we get, you see the error? Yeah. And we get this error. Len is 3, but index is 99, and it's a panic. And it comes from this line where it's the line main rs 45, which is here. Okay, so I need to understand. Okay, now I'm going to put the backtrace. Okay, let's read. Here we're attempting to access the 100th element of our vector, which is at index 99, yes, starting from 0. But the vector is only 3 elements. In this situation, Rust will panic. Using the brackets is supported is supposed to return an element, but if you pass an individual index, there's no element that Rust could return here. That would be correct. In C, attempting to read beyond the end of the data structure is undefined behavior. Yeah, you might get some random data. It's also a security vulnerability. You might get whatever is at the location in memory that would correspond to that element in the data structure, even though the memory doesn't belong to that structure. This is called a buffer overread and can lead to security vulnerabilities. If an attacker is able to manipulate the index in such a way as to read data, they shouldn't be allowed that is stored after the data structure. Yeah, sometimes also the OS might like throw an error or some syscall, something that will just crash your program because you're accessing memory that is not allocated to your application or to your process. To protect your program from this sort of vulnerability, if you try to read an element at the index that doesn't exist, Rust will stop execution and refuse to continue. And this is the error that we got. This error points at line 4 of our main file where we attempt to access index 99. The next note line tells us that we can set the Rust backtrace environment variable to get backtrace of exactly what happened to cause the error. A backtrace is a list of all the functions that have been called. To get to the point, backtraces in Rust work as they do in other languages. The key to reading the backtrace is to start from the top and read until you see files you wrote, that the spot where the problem originated, the lines above that the spot are code that your code has called, the lines below are code that called your code. This before and after lines might include core Rust code, standard library code, or crates that you're using. Let's try getting a backtrace by setting the Rust backtrace environment variable to any value except 0. Okay, so basically this long paragraph tells you that you'll get the call stack in reverse order, I guess, from the error up until your function, your location. Let's see how it goes. Let's put the environment variable. I think it goes like this. Rust backtrace equals 1, and then cargo run. Okay, so as you can see, and I'll scroll this up. I can't scroll this. Weird. So let's clear and then run it again. So now we can see the entire error. So we see that this is where we had the error, right? This is our code. This is probably what runs our code. Something with debugger maybe. Yeah, or the entry or the actual entry point to the program. And then we go to like implementation of I think the index, the brackets, and then the index and panic bound checks. And so here is a code of a panic bound check, and then it formats the panic, and then it fires the panic. I think if I click here, I will not find this file because it's compile the thing into the executable. But we can see where the error originated from. I think because it's in core Rust, then we don't have a lot of information. But if we see something like this in the cargo, because cargos are open source, from what I've seen so far, then we'll be able to figure out where the problem in the code is and maybe try to debug the error using this. Okay, let's continue. And we see a very similar error with different hashes, because probably it's a different version of Rust. That's a lot of output. The exact output you see might be different depending on your operating system and Rust version. In order to get backtraces within this information, debug symbols must be enabled. Debug symbols are enabled by default when using cargo build or cargo run without the release flag, as we have here. In the output listing 9.2, line 6 of the backtrace points to the line in our project that's causing the problem. Line 4, 5, this. If we don't want our program to panic, we should start our investigation at the location pointed to by the first line mentioned a file we wrote in listing 9.1, where we deliberately wrote code that would panic. The way to fix the panic is not to request an element beyond the range of the vector indexes. When your code panics in the future, you'll need to figure out what action the code is taking, with what values to cause the panic, and what the code should do instead. We'll come back to panic and when we should and should not use panic to handle error conditions in the to panic or not to panic section later in this chapter. Next, we'll look at how to recover from an error using result. Okay. Great. Most errors aren't serious enough to require the program to stop entirely. Sometimes when a function fails, it's for a reason that you can easily interpret and respond to. For example, if you try to open a file and that operation fails because the file doesn't exist, you might want to create the file instead of terminating the process. Recall from the handling potential failures with the result in chapter 2. We have the enum of result is defined like this, so we have an OK with a type and an error with a different type. The T and E are generic types parameters. We'll discuss generics in more detail in chapter 10, which is the next chapter. What you need to know right now is that T represents the type of the value that will be returned in a success case within the OK variant, and E represents the type of error that will be returned in a failure case within the error variant. Because result has these generic type parameters, we can use the result type and the functions defined on it in many different situations where the successful value and error value that we want to return may differ. Let's call a function that returns a result value because the function could fail. In listing 9.3, we try to open a file. So let's do this. Let greeting file result equals file open, right, hello txt. And I guess it's going to be an error, right? No. I need to include the standard file, use std as file. Okay. So now I see that the greeting file result is a type of result, file, and error. Okay. The return type of file open is a result. The generic parameter T has been filled in by the implementation of file open with the type of the success value, std file, which is a file handle. The type E used in the error value is stdio error. The return type means the call to file open might succeed and return a file handle that we can read from or write to. The function call also might fail. For example, the file might not exist or we might not have permission to access the file. The file open function needs to have a way to tell us whether it succeeded or failed, and at the same time give us either the file handle or error information. This information exactly what the result enum conveys. In the case where a file open succeeds, the value in this variable greeting file result will be an instance of OK that contains a file handle. In the case where it fails, the value in greeting file result will be an instance of error that contains more information about the kind of error happened. We need to add to the code in listing 9.3 to take different actions depending on value file open returns. Listing 9.4 shows a way to handle the result using a basic tool, the match expression. So we now have let greeting file equals match, right? So we match the greeting file result. If we get an OK with a file handle, then we just return file, right? And if we have an error with an error inside it, then we should panic and problem opening file, right? And we print the file out. Then error, right? And semicolon. Ooh, yes. So let's see. If it's okay, then we return the file handle, and if it's not okay, we just panic with the error. Okay, I wonder. No, I think it's the if equals. Okay, never mind. This is okay just for the example. I think in exercises we'll try something more interesting. Okay, so we have this, and probably now if I run this, it will panic, right? Okay, it's thread main panic, problem opening file W. Yep, that's my typo. Not found. Yeah, code 2, kind not found, method, the system cannot find the file specified. Okay. Let's continue. Note that like the option enum, the result enum, and its variants have been brought into scope by the prelude, so we don't need to specify results before the OK and error variants in the match arms. When the result is OK, the code will return the inner file value out of the OK variant, and we then assign the file handler value to the variable greeting file. After the match, we can use the file handle for reading or writing. The other arm of the match handles the case where we get an error value from file open. In this example, we've chosen to call the panic macro if there is no file named hello.txt in our current directory, and we run this code. We'll see the following output from panic macro. Yeah, let me just set the backtrace back to 0 and run it again to get just this error. Yeah, we got just this error. Okay. As usual, the output tells us exactly what's wrong. Matching on different errors. Okay. So the code in listing 9.4 will panic no matter why. File open failed. However, we want to take different actions for different failure reasons. If file open failed because the file doesn't exist, we want to create the file and return the handle to the new file. If file open failed for any other reason, for example, because we didn't have permissions to open the file, we still want the code to panic in the same way we did in listing 9.4. For this, we add an inner match expression shown in listing 9.5. So now, an error, let's just cut this out. We have a new match for error kind, right? So for error kind, if we have error kind not found, right? If we have a not found here, then we match again the file create hello.txt, right? And then if the file is created successfully, then we just return it, right? And if there's an error, we print the error, right? We panic with the error here. So error creating hello.txt, and we will print the error here, and then if we match error kind other error for all other errors, we have a regular panic, and with other error here. Okay, great. So let's walk through it. If everything is okay, we return a handle. If there's an error, if this error is not found, then we try to create a file. If we successfully created a file, we return it. If we didn't create the file, something was wrong, we panic with this. And if we got an error from the opening file, that's another error, we just do the previous thing. I think now it will just open the file. I think that's what will happen if you run it once. Everything runs and it creates the file. And now if you want to see, we do have an empty hello.txt file. Okay. Let's move on. The type of the value that file open returns inside error variant is IO error, which is a struct provided by the standard library. This struct has a method kind that we can call to get an IO error kind value. The enum IO error kind is provided by the standard library and has variants representing the different kinds of errors that might result from an IO operation. The variant we want to use is error kind not found, which indicates the file we're trying to open doesn't exist yet. So we match the greeting file result, but we also have inner match on error kind. This condition we want to check in the inner match is whatever the value returned from error kind is the not found variant of the error kind enum. If it is, we try to create the file with file create. However, because file create could also fail, we need a second arm in the inner match expression, which the file can't be created. A different error message is printed. The second arm of the outer match stays the same. So the program panics on any error besides the missing file error. Okay. Let's see what other errors we have. Address and use. Okay, a lot of IO errors here. Okay, great. So alternative to using match with result. That's a lot of match. The match expression is very useful, but also very much a primitive. In chapter 13, you learn about closures, which are used within many of the methods defined on result. These methods can be more concise than using match when handling the result value in your code. For example, there's another way to write the same logic as shown in 9.5, this time using closures and the unwrap or else. So we have greeting file, unwrap or else, error. If error kind is this, then file create and unwrap. So basically we're doing unwrap instead of matches here. And the let, instead of this match, we have a file open, and I'm unwrapping. Probably unwrapping returns the value or does something. Okay. Although this code has the same behavior as listing 9.5, it doesn't contain any match expressions and is cleaner to read. I don't know about cleaner, but okay. Come back to this example after you've read chapter 13 and look up the unwrap or else method in the standard library documentation. Many more of these methods can clean up a huge nested match expression when you're dealing with errors. Okay. Shortcuts for panics on error. Unwrap and expect. Yeah, I think we saw expect in chapter 2. Okay, so I think we have a new... No, not exactly new. So now, let's delete the file. I think it expects us to delete the file here. Move it to recycling bin. Let's do this. Okay. So, using match works well enough, but it can be a bit verbose and doesn't always communicate intent well. The result type has many helper methods defined on it to do various more specific tasks. The unwrap method is a shortcut method implemented just like the match expression we wrote in listing 9.4. If the result value is OK variant, unwrap will return the value inside the OK. Okay, so if I do unwrap here, and notice that now it's a result file error. So if I'm doing unwrap here, then we get a file directly. Let's delete this. Okay, let's work unwrap in action. If we run this code without a hello file, we'll see that an error message from panic. Let's see it panic. And it panicked indeed. And we have an error very similar to what we saw before. Practically exactly the same. Okay, so let's continue. Similarly, the expect method lets us also choose the panic error message using expect instead of unwrap. So if I do expect, then I can write my error message. And if I run this, I get somewhere here, my error message instead of something this. Okay. Let's continue. Let's just move the expect here. Okay. The syntax of expect looks like this. Yep. And we use expect in the same way as unwrap to return the file handler or call the panic macro. The error message used by expect in its call to panic will be parameter that we pass to expect rather than the default panic message that unwrap uses. Here's what it looks like. Yep. In production quality code, most stations choose expect rather than the unwrap and give more context about why the operation is expected to always succeed. That way, if your assumptions are ever proven wrong, you have more information to use in debugging. Okay, so basically they use the expect here as some sort of assertion, dynamic assertion. Okay. I don't like assertions in production code. Maybe like in release code where you just want to test everything, that everything works okay after optimizations, but it's like I think final production code should not have any panics in it. When a function propagating errors. When a function's implementation calls something that might fail, instead of handling the error within the function itself, you can return the error to the calling code so that it can decide what to do. This is known as propagating the error and gives more control to the calling code. Where there might be more information or logic that dictates how the error should be handled, that's what you have available in the context of your code. For example, listing 9.6 shows a function that reads a username from a file. If the file doesn't exist or can't be read, the function will return those errors to the code that called the function. Okay, so I'm not going to copy it, but let's go over the code. So we have here a function that returns a result that it returns a string that it reads from the file and an IO error otherwise. So first of all, I'll try to open the file. Right, if there's an error, then I return the error here, and if there's no error, then I put the file in this mutable username file variable. Then I create a mutable username string, and then I try to read. And again, I match the read function, and then if it is okay, then I return the username. And if it's not okay, then I return the error. Pretty much makes sense. This function can be written in a much shorter way, but we're going to start by doing it. We're doing a lot of it manually in order to explore error handling. At the end, we'll show the shorter way. Let's look at the return type of the function first. Result string IO error. That means the function is returning a value of type result, where the generic parameter t has been filled with the concrete type string, and the generic type e has been filled with a concrete type of IO error. If this function succeeds without any problem, the code that calls this function will receive an OK value that holds a string. The username that the function reads from the file If this function encounters any problem, the calling code will receive an error value that holds an instance of IO error that contains more information about what the problem were. We choose IO error as the return type of this function because that happened to be the type of error value returned from both of the operations we're calling in this function's body that might fail, the file open and the read to string methods. The body of the function starts by calling file open function, then we handle the result value with a match similar to the match in listing 9.4. If file open succeeds, the file handle to the pattern. I think they're just describing everything that we saw. I'll continue reading, but I think I'll copy paste the code here so we can reference by looking at the body of the function. Okay, let's see. If file open succeeds, the file handle in the pattern variable file becomes the value in the mutable variable username file, and the function here, and the function continues. If the error case, instead of calling panic, we use the return keyword to return early out of the function entirely and pass the error value from file open. Okay, and here we wrap this IO error again with the error enumeration. Okay, so we have so if we have a file handle in username file, the function then creates a new string in variable username. This is line 12. The read to string method also returns a result because it might fail even though file open succeeded, so we need another match to handle the result to read string. If read to string succeeds, then our function has succeeded and we return the username from that file that's now in username wrapped in an OK. If read to string fails, we return the error value in the same way that we return the value in the match that handled the error value of file open. However, we don't need to explicitly say return because it's the last expression in the function. The code that calls this code will then handle getting either an OK value that contains a username or an error value that contains the IO error. It's up to the calling code to decide what to do with those default with those values. If the calling code gets an error value, it could call panic and crash the program, use a default username, or look up the username from somewhere other than a file. For example, we don't have enough information on what the calling code is actually trying to do, so we propagate all the successes or error information upward for it to handle appropriately. This pattern of propagating errors is so common in Rust that the Rust provides the question mark operator to make this easier. Oh, that's good. Listing 9.7 shows an implementation of read username from file that has the same functionality as in listing 9.6, but this implementation uses the question mark operator. So let's see what's different. So username file, instead of this, we're doing the question mark. So let's see what's the type. So the type of file, I think that just returns the error. The question mark just returns the error. And it's immutable now. It's mutable now, so we don't need this. This instead comes instead of this. And now we create the username, and then we just do this and return the OK username like this. Right. Okay, so no match. Okay, so now what we have here, let's see. So we have the username file. I guess that's if we put a question mark, it just returns the error. So if it can't open the file, it returns the error, and if it can, we have a username file. Then we create a string, and then we try to read the string, and if it fails, we return the error, and if it succeeds, we return the username. Okay. The question mark placed after a result value is defined to work in almost the same way as a match expression we defined to handle the result values in listing 9.6. If the value of the result is an OK, the value inside the OK will get returned from this expression and the program will continue. If the value is an error, the error will be returned from the whole function as if we had used the return keywords, so the error value gets propagated to the calling code. There's a difference between what the match expression from listing 9.6 does and what the question mark operator does. Error values that have the question mark operator called on them go through the from function, defined in the from trait in the standard library, which is used to convert values from one type into another. When question mark operator calls the from function, the error type is converted into the error type defined in the return type of the current function. This is useful when a function returns one error type to represent all the ways a function might fail, even if parts might fail for many different reasons. So basically, the question mark does not return the error, it wraps the error that I'm getting from read to string to fit this error, if it can. I think if it can't, there'll be a compilation error. I don't know enough error types to do. Maybe if I'm trying to do like I32 here, it will fail. Yep, it says that it couldn't convert to I32. Okay, excellent. Okay, for example, we could change the read username from file function listing 9.7 to return a custom error type named RError that we define. If we also define an implementation from IOError or RError to construct an instance of RError from IOError, then the question mark operator calls in the body of the read username from file will call from and convert the error types without needing to add any more code to the function. In the context of listing 9.7, the question mark at the end of the file open call will return the value inside an OK to the variable username file. If an error occurs, the question mark operator will return early out of the whole function and give any error value to the calling code. The same thing applies to the question mark at the end of the read to string call. The question mark operator eliminates a lot of boilerplate and makes the function implementation simpler. We could even shorten this code by further chaining the method calls immediately after the question mark is shown on listing 9. So we're creating the username first, and then we have the file open, right? And we chain it to the read string because I need the file handle here. So we chain it like this, and this is the same. Excellent. In time. Okay, great. We've moved the creation of the new string and username to the beginning of the function. That part hasn't changed. Instead of creating a variable named username file, we've chained the call to read to string directly onto the result of the file open. We still have a question mark at the end of the read to string call, and we still return an OK value containing the username when both file open and read to string succeeded rather than returning errors. The functionality is again the same as listing 9.6 and 9.7. This is just a different, more ergonomic way to write it. Listing 9.9 shows a way to make this even shorter using fs read to string. Okay, I guess that's what fs read to string is all about. Okay, reading a file into string is fairly common operation, so the standard library provides the convenient fs read to string function that opens the file, creates a new string, reads the content of the file, puts the content into that string, and returns it. Of course, using fs read to string doesn't give us the opportunity to explain all the error handling, so we did it the longer way. Okay, where the question mark operator can be used. Okay, the question mark operator can only be used in functions whose return type is compatible with the value the question mark is used on. Yeah, we saw with the I32 before. This is because the question mark operator is defined to perform an early return of value out of the function. In the same manner as a match expression we defined in listing 9.6. In listing 9.6, the match was using a result value, and the early return arm returned an error E value. The return type of the function has to be a result so that it's compatible with the return. In listing 9.10, let's look at the error we get if we use question mark operator in a main function with a return type incompatible with the type of the value we use. So now we have a main function without this, and we should get let's try to do something like this. Let's delete this and get a function main, and we let greeting file equals file open hello.txt, and let's get a question mark here to get a file, and we have an error because the operator question mark can only be used in the function that returns a result. Yeah, exactly what we have here. Okay, this error points out that we've only allowed to use the question mark operator in a function that returns result option or another type that implements from residual. Okay, so it's from residual that what we need. Okay, I think we'll dive deeper into this when we're getting errors left and right when we try to implement things, or maybe there'll be a chapter that goes over this. Okay, to fix this error, you have two choices. One choice is to change the return type of your function to be compatible with the value you're using the question mark operator on, as long as you have no restrictions preventing that. The other technique is to use a match or one of the result methods to handle the result in whatever way is appropriate. The error message also mentioned that question mark can be used with option value as well. As with using question mark on a result, you can only use question on an option in a function that returns an option. The behavior of the question mark operator when called on an option is similar to the behavior when called with a result. If the value is none, the none will be returned early from the function at that point. If the value is sum, the value inside the sum in this resulting value of the expression, and the function continues. Listing 911 has an example of a function that finds last characters of the first line in the given text. So we have this, and if we don't have a next, we'll return a none, and we return the last. Okay, makes sense. Okay, the function returns option character because it's possible that that there is a character there, but it's also possible that there isn't. The code takes the text string slice argument and calls the lines method on it, which returns an iterator of the lines in the string. Because the function wants to examine the first line, it calls next on the iterator to get the first line from the iterator. If text is empty string, this call to next will return a none, in which case we use the question mark to stop and return none from the last character of the first line. If the text is not empty, string next will return some value containing a string slice of the first line in text. I don't think it will return the value itself, not the sum, because of the question mark. The question mark extracts the string slice, and we can call characters on the string slice to get an iterator of its characters. We're interested in the last character of this first line, so we call the last to return the last item in this iterator. This is an option because it's possible that the first line is the empty string. For example, if text starts with a blank line and has characters on other lines, as in like /n hi. However, if there is a last character on the first line, it will be returned in the sum variant. The question mark operator in the middle gives us a concise way to express the logic, allowing us to implement the function in one line. If we couldn't use the question mark operator on option, we'd have to implement this logic using more method call or a match expression. Note that you can use the question mark operator on result in a function that returns result, and you can use the question mark operator on an option in a function that returns option, but you can't mix and match. The question mark operator won't automatically convert a result to an option or vice versa. In those cases, you can use methods like OK method on result or the OK or method on option to do the conversion explicitly. So far, all the main function we've used return the unit. The main function is special because it's the entry and exit point of executables programs, and there are restrictions on what its return type can be for the programmers to behave, for the programs to behave as expected, and the programmers. Luckily, main can also return a result. Listing 912 has the code from listing 910, but we've changed the return type of main to be result. So let's do this. Result unit and box error. What is this? And now it yeah, I need to get the standard error here. Let's do a quick fix. Import error, standard error. Okay, great. And it still has an error here. We have box, we have file, we have error here. Okay, we need to return an OK at the end, probably. Yep. And the OK should be this. Okay, excellent. The box dynamic error type is a trait object, which we'll talk about in the using trait object that allow blah, 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 chapter 17. For now, you can read the box dyn error to mean any kind of error using question mark on the result value in a main function with the error type. This is allowed because it allows any error value to be returned early, even though the body of the main function will only ever return errors for the type standard IO error. By specifying this box dynamic error, this signature will continue to be correct even if code that returns other errors is added to the body of main. When a main function returns a result, the executable will exit with a value of 0 if main is okay, and will exit with a non-zero value if main returns an error value. Executables written in C return integers when they exit. Programs that exit successfully return a 0, and programs that error returns some integer other than 0. Rust also returns integers from the executables to be compatible with this convention. The main function may return any type that implements the standard process termination trait, which contains a function report that returns an exit code. Consult the standard library documentation for more information on implementing that termination trait for your own types. Now that we've discussed the details of calling panic or returning results, let's return to the topic of how to decide which is appropriate to use in which cases. Okay. What's the time here? We're close to an hour. Okay, let's continue. Let's just push through. So, how do you decide when you should call panic and when you should return a result? When code panics, there is no way to recover. You could call panic for any error situation whenever there's a possible way to recover or not. But then you're making a decision that the situation is unrecoverable on behalf of the calling code. When you choose to return a result value, you give the calling code options. The calling code could choose to attempt to recover in a way that's appropriate for its situation, or it could decide that an error value in this case is unrecoverable, so it can call panic and turn your recoverable error into an unrecoverable one. Therefore, returning result is a good default choice when you're defining a function that might fail. In situations such as examples, prototype code, and tests, it's more appropriate to write code that panics instead of returning a result. Let's explore why, then discuss a situation in which the compiler can't tell that the failure is impossible, but you as a human can. The chapter will conclude with some general guidelines on how to decide wherever a panic in library code. Okay, when you're writing an example to illustrate some concept, also including robust error handling code can make the example less clear. In examples, it's understood that the call to a method like unwrap that could panic is meant as a placeholder for the way you'd want your application to handle errors, which can differ based on what the rest of your code is doing. Similarly, the unwrap and expect methods are very handy when prototyping before you're ready to decide how to handle errors. They leave clear markers in your code for when you're ready to make your program more robust. If a method call fails in a test, you'd want the whole test to fail, even if that method isn't the functionality under test, because panic is how a test is marked as a failure. Calling unwrap or expect is exactly what should happen. Okay, case in which you have more information than the compiler. It should also be appropriate to call unwrap or expect when you have some other logic that ensures the result will have an OK value, but the logic isn't something the compiler understands. You'll still have a result value that you need to handle. Whatever operation is calling still has the possibility of failing in general, even though it's logically impossible for your particular situation. If you can ensure by manually inspecting the code that you'll never have an error variant, it's perfectly acceptable to call unwrap and even better, to document the reason you think you'll never get you'll never have an error variant in the expect text. Here's an example. Okay, we take the IP, we parse it, and then expect. Okay, so yeah, this is like static asserts, I think, but it's dynamic. Well, or maybe not. Maybe the compiler knows how to compile it into a static test. We're creating an IP address instance by parsing a hard-coded string. We can see that 127.0.0.1 is a valid IP address, so it's acceptable to use expect here. However, having a hard-coded valid string doesn't change the return type of the parse method. We still get a result value, and the compiler will still make us handle the result as if the error variant is possibly because the compiler isn't smart enough to see that the string is always a valid IP address. If the IP address string came from users rather than being hard-coded into the program, and therefore did have a possibility of failure, we definitely want to handle the result in a more robust way instead. Mentioning the assumption that this IP address is hard-coded will prompt us to change the expect to a better error handling code if in the future we need to get the IP address from other source instead. Okay, guidelines for error handling. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contracts, or invariant has been broken, such as when invalid values, contradictory values, or missing values are passed to your code. Plus one more thing of the following. The bad state is something that's unexpected as opposed to something that will likely happen occasionally, like a user entering data in the wrong format. Your code after this point needs to rely on not being in this bad state rather than checking for your problem at every step. There's not a good way to encode this information in the types you use. We'll work through an example of what it means in chapter 17. If someone calls your code and passes in values that don't make any sense, it's best to return an error if you can, so the user of the library can decide what they want to do in this case. However, in cases where continuing could be insecure or harmful, the best choice might be to call panic and alert the person using your library to the bug in their code so they can fix it during the development. Similarly, panic is often appropriate if you're calling external code that is out of your control and it returns an invalid state that you have no way of fixing. However, when failing is expected, it's more appropriate to return result than to make panic call. Example includes a parser being given malformed data or an HTTP request returning a status that indicates you have hit a rate limit. In these cases, returning a result indicates that the failure is an expected possibility that the calling code must decide on how to handle. When your code performs an operation that could put a user at risk, if it's code using invalid values, your code should verify the values are valid first and panic if the values aren't valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason the standard library will call panic if you attempt an out-of-bound memory access. Trying to access memory that doesn't belong to the current data structure is a common security problem. Functions often have contracts. Their behavior is only guaranteed if the inputs meet particular requirements. Panicking when the contract is valid makes sense because a contract violation always indicates a caller side bug, and it's not a kind of error you want the calling code to have to explicitly handle. In fact, there is no reasonable way for the calling code to recover. The calling programmers need to fix the code. Contracts of a function, especially when violating, will cause a panic, should be explained in API documentation for the function. So yeah, I will retract my previous statement. You can put panics in a library as asserts on inputs. I don't think that internal state errors should panic, but if the user provides something that breaks the API or something that you think the programmer should be alerted and alerted really harshly, then you should panic. I think you still should avoid panicking, especially with with production code, but it's a gray area. Okay. However, having lots of error checks in all your functions would be verbose and annoying Fortunately, you can use Rust's type system and thus type checking done by compiler to do many of the checks for you. If your function has a particular type as a parameter, you can proceed with your code logic knowing that the compiler has already ensured you have a valid value. For example, if you have a type rather than an option, your program expects to have something rather than nothing. Your code then doesn't have to handle two cases for the sum and none variance. It will only have one case for definitely having a value. Code trying to pass nothing to your function won't even compile, so your function doesn't have to check for that case at runtime. Another example is using an unsigned integer such as u32, which ensures the parameter is never negative. Okay. Creating custom type for validation. Let's take the idea of using Rust's type system to ensure we have a valid value one step further and look at creating a custom type for validation. Recall the guessing game in Chapter 2, in which our code asks the user to guess a number between 1 and 100. Whenever validated that user's guess was between those numbers before checking it against our secret number. We only validated that the guess was positive. In this case, the consequences were not very dire. Our option of too high or too low would still be correct, but it could be a useful enhancement to guide the user toward valid guesses and have different behavior when a user guesses a number that's out of range versus when a user types for some, for example, letters. One way to do this would be to parse the guess as I32 instead of U32 to allow potentially negative numbers, and then add a check to the number being in range, like so. So the guess, which is an I32, we parse it as an I32, and we just see if the guess is within range. And okay, the if expression checks whatever value is out of range, tell the user about the problem, and calls continue to start the next iteration of the loop and ask for another guess. After the if expression, we can proceed with a comparison between guess and the secret number, knowing that guess is between 1 and 100. However, this is not an ideal solution. If it was absolutely critical that the program only operated on values between 1 and 100, and it had many functions with this requirement, having a check like this is in every function would be tedious and might impact performance. Instead, we can make a new type and put the validation in the function to create an instance of the type rather than repeating the validation everywhere. That way, it's safe for functions to use a new type in their signature and confidently use the values they receive. Listing 913 shows one way to define a guess type that will only create instances of guess if the new function receives a value between 1 and 100. So we have a struct called guess with a I32, and the implementation has a new, which gets an I32, checks the value, panics if you get the wrong value, else it returns an instance of itself, and then we have a value that just returns a value here. Okay, first we define a struct named guess that has the field named value that holds an I32. This is where the number will be stored. Then we implement an associated function named new on guess that creates the instance of guess values. The new function is defined to have one parameter named value of the type I32 and to return a guess. The code in the body of the new function tests value and makes sure it's between 1 and 100. If value doesn't pass this test, we make a panic call, which will alert the programmer who is writing the calling code that they have a bug they need to fix, because creating a guess with a value outside this range would violate the contract that guess new is relying on. The condition in which guess new might panic should be discussed in its public-facing API documentation. We'll cover documentation conventions indicating the possibility of panic in the API documentation that you create in Chapter 14. If value does pass the test, we create the new guess with its value field set to value parameter and return guess. This is this line. Next, we implement the method named value that borrows self, doesn't have any other parameters, and returns an I32. This kind of method is sometimes called a getter because its purpose is to get some data from a field and return it. This public method is necessary because the value field in our guess struct is private. Yeah. It's important that the value field be private, so code using the guess struct is not allowed to set value directly. Code outside the model must use the new function to create instances of guess, thereby ensuring there is no way of a guess to have a value that hasn't been checked by the conditions in the guess new function. A function that has a parameter or returns only numbers between 1 and 100 could then declare its signature and take that takes or returns a guess rather than an I32 and won't need to do any additional checks in its body. I guess we need to write a parse function as well or something for the guess. Okay, summary. Rust's error handling features are designed to help you write more robust code. The panic macro signals that your program is in a state that it can't handle and lets you lets you tell the process to stop instead of trying to process with individual or incorrect values. The result enums uses Rust's type system to indicate that operations might fail in a way that your code could recover from. You can use the result to tell code that calls your code that it needs to handle potential success or failures as well. Using panic and result in the appropriate situation will make your code more reliable in the face of inevitable problems. Now that you've seen useful ways that the standard library uses generics with the option and result enums, we'll talk about how generic works and how you can use them in your code. That was a very reading intense episode. We've learned about panic, about result, and the question mark. I think that's the only things we've learned about. It's good to know. Now we can handle errors in a more in a better way than we used to until now. So see you next time when we do chapter 10, generics. Thank you.